Okay, let's go ahead and take care of this homework. How many grams of lead are in 500 liters of water with a concentration of 7 ppm? Okay. How do we manage this? What's the equation look like? So we need grams solute, grams solution times 10 to the sixth, and that equals our parts per million. So we have parts per million, and we've got the volume of the solution. Can we figure out what the mass of the solution is? What's the mass of 500 liters of water? A thousand? 500,000? Yeah, so if we convert it into milliliters, we'd have 500,000 milliliters. And each milliliter is equal to a gram since we're talking about water and the density is 1. So pretty simple with that. So then we're going to end up with grams of, in this case, lead divided by 500,000 grams of solution times a million equals 7 ppm. So my grams of lead will end up equaling 7 times 500,000 divided by a million. So is that 3.5 or 35? 35? So 35 grams of PB. Does anybody know why that might be, what's significant about that? The 7 is the maximum allowable level. And then the 500 liters is about what a person drinks of water per year. So you'd be eating about 35 grams of lead per year on average, and still be within the illegal allowable limits. So not really so good. All right, how about the next one? List the following in order of best to worst electrolyte, and then explain why. So who's the best electrolyte? The calcium chloride will give us 3, so that's going to be the best. How about the worst? The barium sulfate gives us 0 because it doesn't break apart, so it's a non-electrolyte. And then the other two? They're tied. They both break up into 2 pieces, so there isn't anything different about them other than the fact that they're different molecules, but they both have 1 positive ion and 1 negative ion. So I'd write calcium chloride, and then maybe potassium nitrate and sodium bromide tied, and then barium sulfate last. Okay, from the most recent set of notes, we had an explanation as to why chemical reactions occur. So what are those 2 reasons? So reduce the amount of energy. If a chemical reaction reduces the amount of energy, then that wants to happen. Nature wants that to happen. And if I can increase the what? Chaos, the disorder, so the entropy. So these are both these 2 things are termed the H. If the H goes down and the S goes up, the enthalpy goes down and the entropy goes up, then that is something which would drive a chemical reaction. And diamonds are not forever. Why? I'm sorry, say that again?
Is not eventually decay.
How come? Use the last question as a reason, as your reasoning for the next answer. Because diamonds are ordered, right? They're very organized, and nature doesn't want that. So slowly over time, it'll become disordered. Okay, entropy. It's a measure of disorder, and its symbol is an S, and its units are usually kilojoules per mole times Kelvin. Just again, want to make sure that we're realizing that it's a measure of the disorder, not the order. So the more chaotic it is, the more entropy you have. And the enthalpy, what's that measure? Heat. Okay. And its symbol is an H, and its units are kilojoules per mole. Okay. And free energy? I don't know if that's actually a word, but sure. And its symbol is a G. And it's also kilojoules per mole, most likely. Spontaneousness. That might be a word. A given reaction is endothermic and becomes more disordered. Is this spontaneous reaction? Explain your answer. So it's endothermic and it becomes more ordered. So what does that first word there mean, endothermic?
Absorption of heat.
Bringing energy in. So endo and exo are opposites of each other. So we have an endoskeleton and an ant has an exoskeleton. So this would be endo, inside, and thermic heat. So it's bringing heat or energy into it. And it also becomes more ordered. So is that spontaneous or non-spontaneous? No, it's not spontaneous, right? Because this is the opposite of what nature's looking for. This is gaining energy and becoming ordered, and that's backwards. So, nope. This problem is a little tricky, but not a lot tricky, just a little tricky. So the equation for this is that delta G is equal to delta H minus T delta S. What's the tricky part of this problem? One, you got to make sure you got to remember to transform that 19 degrees Celsius into Kelvin. So 19 plus 273, 292 K. Okay. Anything else? What's the other piece? The delta H is in units of what? Kilojoules per mole. And the S is in units of joules per mole. So you either have to have them both be kilojoules or both be joules. I'm going to make them both joules because it's easier to make the bigger number bigger, or the kilo number bigger. So what would 4.1 kilojoules turn into if I made it joules? 4,100 joules. Just move the decimal place over 3 spots. Okay, so for this equation, my delta G is going to be equal to 4,100 joules per mole. And I'm going to subtract off 292K and 12 joules per mole Kelvin. So the kelvins cancel out, and I can do the math for this. All right, so we got 4,100 minus 292 times 12 divided by nothing. And my answer works out to be 596 joules per mole. Sig figs would make us go, well, 6.0 times 10 to the second. I'll just leave it like this. Is this reaction spontaneous at this temperature? It is not. How do you know that it is not? Yep, my delta G is a positive value, so it's not, this reaction will not happen without having energy put into it. So let's do the second one here. So I'm going to add 273 to this, 351 Kelvin this time. So we'll do the same thing, 4,100 joules per mole minus this time 351 K and 12 joules mole Kelvin. Kelvins cancel. I get 351. This time I get negative 112 joules per mole. So not spontaneous here, yes, spontaneous here. Because we became negative when we did it that way.
Can we just answer that using the chart?
Nope, you can't. Why not? Why not? Tell me how you would answer that using the chart.
Up top it gives us the H and the S, and they're both positive, and on the chart, both positive means that it's spontaneous, or it's not spontaneous.
Nope, chart doesn't say that.
So do we need to figure out the temperature? Is that why we can't do it without that?
Yep. There would be a time when you could just use that chart, but this isn't one of those times. When could you use the chart to answer that question?
When temperature is irrelevant?
When temperature is irrelevant. That's the only time. So the question before this one, look at that one. A given reaction is endothermic and becomes more ordered. So is it possible to answer this question without doing math? Yep. Because under no circumstances, regardless of what temperature is, can this be anything except for a non-spontaneous reaction. But in this case, the two, the entropy and the enthalpy are fighting each other. And so then temperature does play a role. So you actually do have to do the math.
And we can't just use the temperature that we're given, 19 degrees Celsius, or the Kelvin.
Yeah, we did do that.
Well, I know, but use that as the temperature. We don't have to use any. Why do we have to use the math to get to joules per mole if we already have 19 degrees Celsius as our temperature? That doesn't make sense.
I don't understand your question.
Okay, never mind. That's all right.
This question asks you if this reaction is spontaneous or not. You can't answer that question to me just by knowing that it's 19 degrees Celsius. You have to actually, I mean, this is what Gibbs did. This was what his work was. That this value right here, you have to calculate it to be positive or negative. And this isn't enough information. That's just telling you what the temperature is. But I'm going to need to actually know how the energy input or output and how the order changes to know if this is going to be spontaneous or not. So you have to do this math for this one. The only time you wouldn't have to do the math to answer this question of spontaneity is if one was positive and one was negative, or one was negative and one was positive. There are only two times on that chart when the temperature is irrelevant. I don't feel like you're happy with that, but
No, it's okay.
all right. Explain how you would make 500.0 milliliters of a 2.5 molar hydrochloric acid solution given 2.5 liters of 12.1 molar hydrochloric acid solution. Okay. What kind of question is this? This is a dilution equation. Are we okay with that? You do not need to know any moles. You don't need to look at the periodic table for this one. What's the extraneous piece of information in this question? The 2.5 liters of 12 molar hydrochloric acid. It's extraneous in the fact that unless I need to use more than 2.5 moles to do the liters to do the problem, then that's the only time it would be. But as long as my value doesn't go over 2.5, I don't really care. So in this problem here, if I'm going to use the dilution equation, then it's going to be M1 V1, M2 V2, and what piece don't we know? We don't know V1. That's the only piece we don't know. What I know is how concentrated the stuff is that I have. I know the concentration and the volume of what I want. I just don't know how much of the concentrated stuff I need to put into the container. So let's say that you only wanted to make 1 glass of orange juice and you had a can of frozen concentrated orange juice. Would you use the whole can? Or just use a spoon and scoop out a couple of, you'd eventually figure out what would be a good amount. So in this case, I'm just looking for the volume of the concentrated stuff. So my volume of my concentrated is going to be 0.25 molar times 500 milliliters divided by 12.1 molar. And okay, so I haven't actually answered the question yet. How do you answer this? Get that amount of HCl, add to 500 milliliter vol flask, fill to the line, and of course you're going to probably want to use a little pipette to make sure that you're super accurate with filling to the line. But when you get a question like, how do you make this? I'm not just looking for the calculation. I want you to tell me how you would actually make it. How does this next question differ from the previous question? The last question is, I started off with a solution. So then I'm using the dilution equation. And then this question is starting off with a solid. And so then I'm going to actually have to figure out what the moles are and grams per mole are for the sodium hydrogen carbonate. What's the other name for sodium hydrogen carbonate? Baking soda, yeah. And then the other chemically kind of name for it is sodium bicarbonate. That bi used to mean hydrogen attached to a carbonate. Or a other polyatomic ion. So I want to make 500 milliliters of this. I want it to be 2.5 molar. And I need to know how much of the solid baking soda I need to add to this. Okay, so I need grams. And I don't have any grams at all. So I need to get myself some grams. So I'm going to write 1.25 moles per liter. I'm going to get rid of the liters by writing 0.5 liters here, and then that'll cancel out. Now I need to get rid of the moles. 1 mole does anybody have a mass for the 84?
We okay with 84?
That sound right? Sorry, I'm just gonna. Two people say 84. We'll go with that. So I've got 84.0066. And then if I do the math for that, it looks like this is upside down. $1.25 times 0.5 times 84.0066. 84. And that's it. Okay, so how's that? That is how you would make that. Save that. What is this? 5.